Okay, so let us start. Now, we start with waves and particles. I will briefly summarize what is known about waves and particles, let us say 100 years ago, and then compare new information that we have learned later. So, according to classical physics, this means let us say 120 years ago, near the beginning of 1900, scientists thought that they have discovered everything at that time. This is the beginning of 1900. And what they claimed about waves and particles, first about waves, interference of waves, both constructive and destructive, and related with the interference phenomena is diffraction, from surfaces of crystals. And in explaining all of these properties, the most important property of wave is its wavelength. Wavelength, lambda, is the characteristic property. All right. You see that when we discuss waves, according to classical ideas, there is no concept of where the wave is. Where is the location of the wave? It's spread all over. And then there is no concept like counting how many waves there are. And now, in sharp contrast to particles, so let us list particles. Major properties. Each particle has a mass. Like these chalks here, this eraser, these are particles and they have masses. Please note that there is no notion about mass regarding waves. Another important property is well-defined position in space. Like you say that this eraser is at this point on the desk, and you can describe its location, its position. Similarly, these chalks here, they are all particles, and they have well-defined positions in space. In fact, it is believed, scientists believed at that time, that it should be possible to measure the location, the position of a particle exactly in space. A third important property of particles is linear momentum. Linear momentum is a vector quantity. It is related to the velocity of the particle by this relation. Mass of the particle times velocity of the particle. And related with momentum, when we have more than one particle, let's say here are two different types of particles. One is a white chalk and the other is a red chalk, two particles. The total momenta here, if we call one of them P1, and the linear momentum of the second one, P2. This is the total momentum of the system, all right? Now, imagine these two particles collide, hit each other. After collision, their momenta change. If you call the new momentum after collision P1 prime and P2 prime, there is a principle called conservation of momentum, linear momentum. It says that the total momentum before collision is the same as the total after collision. This is similar to the principle of conservation of energy. The total energy before, the total energy doesn't change, right? It's a principle similar, but this time using the linear momenta. Another very interesting, actually obvious property of particles is that we can count them. Like, if you see the chalks here, you can say 1, 2, 3, 4, 5, 6. There are 6 chalks on the desk. We can count particles. This is a simple, obvious property, but it is important because it's not present over there, according to classical ideas for waves. Waves, we cannot count them according to classical ideas. Okay, now we come to modern views. Modern views emerged after 1900s. In fact, quite short time actually, between 1900 and 1930, let us say, in 30 years. Quite new concepts have been developed. Of course, everything we claim is based upon experiments. In science, only if experimental observation, when you do some suitable experiments, if you observe something and if it is repeatable, then you can say that you have observed a certain property. So in this sense, experiments which have been performed for waves indicated that in addition to these properties, waves may also have some particle properties. What are they? Some of these, not all of it, but some. For example, we will see that waves could also have linear momentum. Normally, it's a particle property. And it will obey this principle and also countable. Waves, depending on the type of experiment you do, you can count. All right. Similarly, experiments done using particles have indicated that particles may also have wave properties. What is a major property? It is wavelength, lambda. So it turns out particles could also be associated with a wavelength, given a numerical value for the wavelength. So let us discuss some of those. Now, first, well, the properties that we are going to discuss arose from experiments in which light is used together with some particles. In other words, interaction of light with particles. And in this interaction, energy can be transferred from light to the particles, and also momentum can be transferred from light to particles. And analyzing such experiments, we can determine some additional properties. So let us look at light according to the classical ideas. First of all, light is a form of energy. Form of energy that behaves like a wave. As any wave, light is characterized by a wavelength, and observations show that values of wavelengths is infinite. And each different value of wavelength means a different type of light. If one analyzes the light which comes from the sun to the earth, some of them our eyes can see them. That part is called the visible part. Lambda between 400 and 700 nanometer for lights which have wavelengths between this range, 400 and 700, human eye can detect it. And to our eye, each lambda value of light appears as color. For example, light with wavelength 700 nanometer appears to human eye as red light. This is and this one is violet color. And in between, we have all the colors of the rainbow. Now, light can be artificially generated, or it can be obtained from the sunlight. And it turns out that in addition to these wavelengths, there are lights of wavelength smaller and smaller than 400 nanometers, and also much longer than 700 nanometers. Therefore, this range of possibilities for the wavelength is called spectrum, electromagnetic spectrum. When we examine all of it together, it's a very large range. Now, regardless of the wavelength of the light wave, it turns out, experiment shows it, the speed of light in vacuum, in empty space, is the same for all wavelengths. And the speed of light is commonly denoted by the letter c. And this c is about 3 times 10 to the 8 meters per second. So light with any wavelength travels in empty space, in vacuum, with the same speed. And as you know, whenever we have a wave, we also talk about frequency of the wave. Frequency this is the symbol which commonly represents, or it is used to mean the frequency of the wave. Greek letter nu, and wavelength times frequency is the same for all kinds of light waves. This expression means that lambda and frequency are not independent. Therefore, to characterize a light wave, you may use either its wavelength or you may use its frequency, because it means the same thing, because if you know the wavelength, this expression tells you what the frequency is. Frequency is c over lambda. Or if frequency is given, then wavelength is c over frequency. Therefore, just one piece of information, either wavelength or frequency, is sufficient to characterize the light wave. Let us note the units also. The SI units. SI, standard international units. Meter, kilogram, second. All right, these are the main units. Wavelength has distance unit, and the SI unit is meter. Frequency has 1 over second unit. As you see from the expression, meter times 1 over second means meter over second, meter per second, and that's the unit of C, as you see here, meter per second. This 1 over second is sometimes indicated by this symbol, S minus 1, or it's also this unit, Hertz, Hz unit. This symbol, rather, is also used to mean 1 over second. All right. Now, here is a sample of particles in a container. The particles here could be atoms, or molecules, or electrons, or neutrons, anything. And this is a light wave, or light beam. Experiments which are designed to study properties of light waves are this type. We have a light source which produces a light beam, and then we have a sample, usually gas, in the gas phase. The container is filled with some particles here, and then here this light passes through the sample, and then there is a detector on the other side which analyzes what happens to the light wave. All right? And by interpreting the results, one obtains information about both the particles in the container, in the sample, and also some properties for the light wave. Now, when the beam passes through the sample here, it is found that energy exchange takes place from the light beam to the particles of the sample. Now, the analysis, the interpretation of this energy transfer from the light beam to the particles in the sample indicates that we have to regard the light beam as a collection of tiny energy packets. So this light beam these are energy packets, each one, this one, that one, that one. And assuming the light beam has a single frequency, such a light is called monochromatic light, just one frequency. And each one of these energy packets is called a photon. There are many photons in the light beam. All of these photons move in the same direction, and the direction of the motion is the same as the direction of the light. If light is shining to the right, then the photons are traveling in the same direction. Now, each photon carries energy, and again, everything I'm summarizing here is based upon experimental observation and the consequent interpretation. The photon energy is directly proportional to frequency of the light. The proportionality constant is commonly denoted by the h symbol, small h. So when you see this expression, you should imagine that if frequency is different, we have a different type of light. All right? Like corresponding to all of the visible range from 400 to 700. As you change the wavelength, that means the corresponding frequency is also changing. Now, the frequency can be different here, but this h is the same for all types of light waves. And the corresponding photon will have a different energy. As you see here, larger frequencies for the light means larger photon energies. That's something you should keep in mind. Well, I'll give you some more examples out of the visible range. There is a part of the wavelengths which is called microwave region. Another part called infrared region. Infrared is usually shortened as IR. IR, infrared. The wavelengths for the infrared are even longer than the 700. Just after that is infrared. That means frequencies are smaller than relative to the visible range. Microwave wavelengths are even longer than infrared. That means their photon light frequencies are much smaller. On the other side, we are examining the range of possible light waves using frequency. Larger frequencies than the violet end are called ultraviolet or UV. So UV photons, if you look at this expression, UV photons means frequencies are larger than visible light. UV photons have more energy than visible light. If you look at the other end, infrared photons have smaller or larger energy than visible light. Infrared photons have smaller frequencies, therefore their energies are also smaller than visible light. Microwave photons are even smaller. All right, so this result is very important, of course. Now, please note that this energy is the energy of just one of these particles. Each one is a photon. Each symbol is a photon here. Each one has this energy here. All right? The total energy that the light carries is just, because this is a monochromatic one frequency light, energy of a photon, one photon, multiplied by number of photons in the beam. All right. Now, this picture is showing you that light waves have a particle property. What is that? Which particle property is that? That it is possible to count how many photons there are in the light beam. Normally, this countability is a particle property, but the results of such experiments, which force us that we have to treat light as a collection of photons, is telling us that light waves in such experiments, in the energy transfer experiments, have a particle property, which means we can count how many photons there are. All right. Now, to connect the photon energy, number of photons, to the total energy carried by the light beam, let us remember the intensity I of a light wave. This is the amount of energy, amount of light energy crossing unit area per unit time. If the light is traveling from right to left, this way, you imagine a area, such as this paper here. This area is perpendicular to the direction of the light. Light is coming this way, all right? And the area is perpendicular. And then, if we use SI units, you imagine 1 square meter area, and then in 1 second, how much energy has crossed. That quantity is called intensity of a light wave. Intensity of a wave is independent of its wavelength or frequency. So they are different things, all right? Like I just mentioned, for light wave, frequency and wavelength are not independent. If you know one of them, you know the other one also. But if you know the frequency or wavelength, you cannot know what the intensity is. Intensity is something different. All right. If we imagine, if the intensity is given to us, and if we ask the question, how much energy has passed, has crossed the unit area in just 1 second, then time times the intensity, 1 times I, gives us numerical value of the total energy that has crossed. That energy, if we call light energy, this is the light energy that has crossed unit area or 1 square meters in just 1 second, the total energy. This total energy must be equal to energy of a single photon, one of these, times number of identical photons. If you call them n, n is the number of photons in the beam, times energy of just 1 photon, because they are all identical photons, we will obtain the total energy which has crossed the unit area, which is in 1 second, which is the total energy of the light. Now, here, this is known. This is intensity times one second, or I have illustrated this for 1 second, but it could, for time, you may take any value you want. You may say in 10 seconds, then you multiply 10 times intensity, because that will give you the total energy that has crossed after 10 seconds. Here I'm just indicating for 1 second. This is known. The frequency is also known for the light wave. Then this expression will tell you numerical value of this n. N is the number of photons, which means how many. But how many means we are talking about a particle property. Just like how many chalks there are on the table here. 1, 2, 3, 4, 5. 5 chalks. That's normally a particle property, but here we are talking about light wave. But to explain this experiment here, the transfer of energy from light to the material particle, we have to accept that photons are present and they can be counted. All right, We are going to give 10 minutes break and continue after that.